So, kia ora everyone. My name is Stacey Middleton and I'm a recent master's graduate from the University of Auckland. This presentation, as you can see, is titled Photogrammetry and the Quantification of Volume in Stone Artefact Analysis, Experimental Improvements to the Volume Ratio. This research discusses the use of photogrammetry as a tool to explore improvements to the calculation of volume in stone artefact analysis. And this is a accumulation of my honours and dissertation work supervised by Rebecca Phillipps and Simon Holdaway. So as has been summed up nicely in the first talk, photogrammetry has had variable applications in archaeology. Currently, this is predominantly in the visualization of excavations and artifacts. More recently, there has been a push towards using photogrammetry as a tool for quantification in excavations and stone artifact analysis. Current studies have focused on analysis at the artifact level using morphometric analysis to explore evidence of use or manufacture, or classification based on artifact form using the morphometric analysis. While these have provided valuable tools to preserve artifacts for future comparative studies and for community outreach, research that poses questions at the assemblage level to explore and compare formation of assemblages has been less intensively explored. The complexity of assemblage formation means material can be moved, recycled, or discarded at any stage of its life history. This results in the creation of palimpsests that emerge when materials from different contexts, discard events, and formation stages become related through final discard location. Photogrammetry can be used in this theoretical context to improve methods that explore variability in the formation and composition of stone artifact assemblages. So the volume ratio is a method that uses the transport of material as a proxy for the movement of people. This method does not rely on the concept of assemblage completeness discussed by Turk and colleagues. This concept describes the assumption of some stone artifact analyses that the total products of reduction remain in a single location. So the volume ratio measures movement specific to stone artifacts and movement related to the cumulative discard of material at a given location. This method thus provides a quantitative measure of movement comparable across assemblages and sites. This is a method similar to the cortex ratio that utilizes volume rather than cortex and surface area to calculate the amount of material expected in an assemblage. The volume ratio is calculated by dividing the total assemblage volume by the modeled assemblage volume. So the total assemblage volume is the cumulative volume of the flake, cores, and tools in an assemblage, and this will be discussed further on the next slide. The modeled assemblage volume is the modeled volume of a stone used for producing flakes. This can either be calculated using generic volume from raw material surveys or the reconstruction of the original nodule volume based on the exhausted cores in an assemblage. The modeled assemblage volume is calculated by multiplying the modeled original nodule volume by the number of cores in an assemblage. This research explores methods to improve the calculation of total assemblage volume using photogrammetry as a tool to compare accuracy. The modeled assemblage volume is also explored using photogrammetry. This method will be briefly discussed at the end, however, there won't be time to discuss results in depth in this presentation. So previously, total assemblage volume has been calculated using three main approaches, being mathematical formulas, density, either using a standardized or individual object densities through hydrostatic weighing, and photogrammetry or laser scanning. Density, either using a standardized, the use of mathematical formulas to calculate total assemblage volume has been calculated using metrics substituted into geometric formulas for flake shape as shown in the first figure. However, work by Lin and colleagues in 2010 has shown this method tends to under or overestimate the volume of an assemblage. Subsequent experimental work has proposed the use of density derived through hydrostatic weighing to calculate volume. This provides accurate quantification of total assemblage volume. However, it is time consuming and requires artifacts to be submerged in water, which is not ideal. Dibble and colleagues in 2005 presented the use of a standardized density of 2.46 to calculate volume for chert and obsidian. These methods of volume quantification are tested to see whether a mathematical formula, density, or a standardized density could be used to improve the calculation of total assemblage volume when compared to volume calculated using photogrammetry. So the first experiment was conducted on a sample of Australian material from an experimental assemblage napped by Douglas and colleagues, composed of 2 cores and 65 flakes. This experiment aimed to test the accuracy of two different methods of calculating volume compared to photogrammetry. The dimensions of each object were measured to insert into the mathematical formulas for volume. The air and water weight were also measured using hydrostatic weighing, and these were compared to photogrammetry as a baseline. 3D models were also constructed for each flake and core, and this was based on Porter and colleagues' method. The second experiment was conducted on a reference collection of 227 flakes and cores collected by Moore and colleagues, and an archaeological sample of 665 obsidian artifacts from Waitapu, Ahuahu, Great Mercury Island that had been sourced using PXRF. This experiment aimed to test the effect of a standardized density on the accuracy of calculating total assemblage volume compared to hydrostatic weighing. The water and air weight were measured for these objects and compared against the volume calculated using the air weights and a standardized density of 2.46. The New Zealand sources of obsidian are known to vary in density, so the intra and inter-source variability of chert and obsidian were compared. A third experiment was also conducted on 3 chert cobbles from Ahuahu, Great Mercury Island, related to the exploration of the modelled nodule volume through experimental work. This will be discussed in brief detail at the end of the total assemblage volume results. So the 3D modelled volume was the volume of each object calculated by measuring the mesh of each photogrammetric model in Blender. These volumes were used as a baseline to compare the accuracy of calculated volume using 3D shape formulas for flake and core classes. So this table here shows the percentage of average difference between volume calculated using photogrammetry and volume calculated using mathematical formulas. The results show that on average, formulas tend to overestimate volume. These overestimations are moderate for proximal and distal and complete flakes with normal and blade forms. Calculations are overestimated by less than 100% of the modelled flake volume. The overestimations for angular fragments and complete flakes with expanding forms are relatively high, with estimations more than 100% of the modelled flake volume. Cores have a comparatively low overestimation, with calculated volume overestimated by 12%. These small differences between core calculation and modelled core measurements reflect findings by other studies investigating differences in calculations such as surface area by Lin and colleagues. While formulas tend to overestimate volume, there is one category that tends to underestimate flake volume. The complete flake class with contracting form tends to underestimate flake volume by 38% of the modelled volume. And so when this comes to the volume ratio, this isn't ideal when you want an accurate total assemblage volume. This figure shows the relationship between flake volume and the percentage of average difference between volume calculated using photogrammetry and volume calculated using mathematical formulas. As the figure shows, when plotted, the difference is highly variable, particularly for smaller flakes. Differences in volume estimations have implications for the calculation of the volume ratio. A paired t-test was conducted to test whether the high percentage differences between formulas and model volume estimates were significant, and it was. This result indicates that the difference between calculated volume and model volume are significantly different, resulting in an inaccurate total assemblage volume likely to inaccurately reflect the amount of material moved in an assemblage. The experimental density results show that chert ranges from a density of 1.1 at the minimum to 3.1 at the maximum density, with variability in between these. Kuatunu, Puhi, Waiari, and Whatuwhiwhi are the exception to this variability due to the smaller sample sizes and therefore less range. Karakonui is a notable source in the sample with the highest variability of density ranging from 1.9 to 3.1. Most chert source densities lie between 2.25 and 2.75, with Opunoni as another exception that has an average range shifted lower than most other sources, but this does not extend below the Karakonui range. Most sources are centered around 2.5, with the exception of Karakonui and Opunoni, whose centers are shifted lower than most other sources. The volumes for chert using standardized density values are highly correlated with the actual volume of flakes measured using hydrostatic weighing. The R value of 0.99 indicates a very strong relationship with a significant p-value. Despite the variability in source density, the percentage difference between total assemblage volume using hydrostatic weighing and total assemblage volume using a standardized value is 1.2%. And a 2-sample Kolmogorov-Smirnov test shows there is no significant difference between the two. That's not super surprising given the nature of what we're measuring. So what does this mean for total assemblage volume? For the overall calculation, this provides a difference of 19,011 millimeters cubed between standardized and non-standardized density. Again, so what does this mean? While this may seem like a large difference, if we treat the volume calculated using hydrostatic weighing as an accurate modeled assemblage volume and the standardized density as the total assemblage volume, this provides a volume ratio of 1, meaning all material is present and the total assemblage volume is being accurately measured. This shows that despite the differences in total assemblage volume, this still provides an accurate volume ratio. The experimental density results for obsidian show ranges from 2.1 at the minimum to 3 at the maximum value. This range is less than chirp. There is still some variability evident, particularly for Mayor Island and Hahe. Mayor Island ranges from 2.1 to 3 and Hahe ranges from 2.1 to 2.7. Most source densities for obsidian lie between 2.25 and 2.5, with outliers from Hahe and Mayor Island beyond this range. Again, this relationship between standardized obsidian volumes and hydrostatic weighed volumes shows similar results to chirp, with an R value of 0.99 indicating a very strong relationship, and again, a significant p-value. The percentage difference between total assemblage volume calculated using hydrostatic weighing and a standardized value is 3.5%. And again, a 2-sample Kolmogorov-Smirnov test shows there is no significant difference between these two methods. For the overall calculation, again, if we contextualize it, this provides a difference of 73,985 millimeters cubed between standardized and non-standardized density. Again, while this may seem like a large difference, if we again treat the volume calculated using hydrostatic weighing as an accurate modeled assemblage volume and the standardized density as the total assemblage volume, this provides a volume ratio of 1. Again, despite the differences in total assemblage volume, this still provides an accurate volume ratio. So although the results aren't discussed in detail here, photogrammetry was also used to explore improvements to the modelling of original nodule volume. 3 chert cores were reduced with 3 different knapping goals that were reflexively altered to suit the quality of the chert nodule. The goal of this experiment was to quantify the loss of volume throughout the reduction process to retrospectively reconstruct original nodule volume based on landmarks or metrics of the exhausted core. Aspects of the core, such as weight, volume, negative flake scars, mathematical formula, and maximum dimensions were used to explore ways to calculate the original volume of the stone that was reduced. A photogrammetric model was made after each reduction attempt, and this was defined as the strike of the core with a hammerstone. The mesh of each model was measured, again using Blender, to quantify the volume of the nodule throughout the reduction process and measure rates of volume loss. As you can see in the figure, each chert nodule had a unique rate of volume reduction due to the internal quality of the material. Of particular note are the steep drops in the rate of core 1 and 3, where the core split in half during the reduction process. These results have implications for the reconstruction of original nodule volume, which won't be discussed today. So to summarize, photogrammetry provides an invaluable tool beyond visualization to aid in the quantification of and improvements to assemblage level analysis in stone artifact studies. For the volume ratio, this has resulted in improvements to the efficiency and accuracy of the calculation of total assemblage volume. This research demonstrates how photogrammetry can be used in archaeological research to answer broad questions related to the formation and composition of stone artifact assemblages. Ngā mihi, and I'm happy to answer any questions.